Cylindrical coordinates are one of the three-dimensional analogs of polar coordinates. Another is spherical, but we won't discuss those because we don't have time. Cylindrical coordinates are used when doing a triple integral in which the projection of the region onto one of the coordinate planes is a good polar region. The best way to explain this is with examples. So we want to find the mass of this ice cream cone region. The red surface is the cone z is equal to the square root of x squared plus y squared. The blue surface is the sphere given by x squared plus y squared plus z squared is equal to 50. And the mass density is z times x squared plus y squared. So what we want to do is do a triple integral over this region, and we want to integrate the function z times x squared plus y squared. And for now, I'll just write dv. Now we have to pick an order of integration. So I'm going to do z on the inside, and that means that the outer two integrals are the xy integrals. And the idea is that we just want to convert this to polar coordinates. The z stays the same, the xy integrals get converted to polar coordinate integrals. And I'll give an explanation on how to do that. So step 1 is to project this region onto the xy plane, and that will help us figure out what the polar region is. So I think it's clear, you might have to think about it, but I think that it's clear that the projection of this shape or this region onto the xy plane is going to be a circle. Now we just need to figure out what the equation of that circle is going to be. So the idea is that when the red and blue surfaces meet, the z values are going to be the same. So in other words, the square root of x squared plus y squared is going to be equal to 50 minus x squared minus y squared. This is the equation for the cone. This is the equation for the sphere if you solve this for z. Now, if you take the square of both sides, you end up with x squared plus y squared is equal to 50 minus x squared minus y squared. Or in other words, this is 50 is equal to 2 times x squared plus y squared, or 25 is equal to x squared plus y squared. So in the xy plane, you get a circle of radius 5 centered at the origin. This is the projection of this region onto the xy plane. Now, for every fixed value in the xy plane, the z values are going to go from a point on the cone to a point on the sphere. So if you have a fixed point in the circle, the z values are going to go from the cone to the sphere. That is, z is going to go from z is equal to the square root of x squared plus y squared, which is just equal to r in polar coordinates, and then it's going to go up to the sphere, which is the square root of 50 minus x squared minus y squared, which is just equal to the square root of 50 minus r squared in polar coordinates. So using all of this, we can now determine what the integral will be. For the outer two integrals, this is the part of the integral in the xy plane, and we're doing polar coordinates. And theta goes from 0 to 2 pi. R will go, for every fixed value of theta, R will go from 0 to 5. And as we discussed here, for every fixed value of theta and R, Z is going to go from R to the square root of 50 minus R squared. And so the function that we're integrating is Z. The function that we're integrating is Z times x squared plus y squared. that's just z times r squared. Then we have to write dz, and normally in these parentheses we'd write dx dy, but we're doing polar coordinates, so it's r dr d theta. But really we don't want to put the r there, we want to put the r outside of the parentheses. So the standard way to do it is to write it like this: r dz dr d theta. And then we can write this as theta equals 0 to 2 pi, r equals 0 to 5. Then the integral z is equal to r to the square root of 50 minus r squared, z r cubed dz dr d theta. And now this is an integral that we can do. So this is the integral. Theta equals 0 to 2 pi. R is equal to 0 to 5. Now for the z integral, the antiderivative of z is z squared over 2. So I'll write the r cubed, z squared over 2, 1/2, and we're going from the square root of 50 minus r squared to r. So this is 50 minus r squared dr d theta. So this is equal to 1/2 the integral theta equals 0 to 2 pi times the integral r is equal to 0 to 5, 50r cubed minus r to the power of 5 dr d theta. And I will let you finish this on your own. This is equal to 5 to the power of 6 over 6 times pi. Okay, so the bottom line here is that when doing cylindrical coordinates, we take the projection of the region onto one of the coordinate planes. It could be the xy plane, the zy plane. In this case, it was the xy plane. It could be the yz plane, any of the 3 coordinate planes. If that is a good polar region, then we want to try cylindrical coordinates. And so in this problem, we just kept the z coordinate the same, and the x and y became polar coordinates. So remember, that's what cylindrical coordinates are.